We'll talk a little bit about conservation of energy. You know what conservation is. You know conservation of mass from chemistry. Mass is never created or destroyed. Well, same thing goes for energy. So we keep all the energy we have in a system, generally, though we do change forms. That means that energy is a conserved quantity. We do change forms a lot. This is the whole basis of roller coasters. Roller coasters conserve most mechanical energy, not all of it. There's lots, and we'll talk about that in a second. But we go from that first hill, where we have lots of gravitational energy. We convert that to kinetic energy, which takes us up the second hill. We now have gravitational energy again, which we convert to kinetic energy, on and on and on and on. You get it. We can't create it or destroy it, and that's important. We talk about loss of energy in a system, and it's not really loss. It's conversion to forms that are harder to capture and measure, and that's what we see in roller coasters, too. Talked about kinetic and potential energy. Oh, potent tail? Who writes these things? Okay, potential energy of objects. What we've really been talking about the whole time is mechanical energy. So mechanical energy is the sum of kinetic energy and all forms of potential energy, gravitational, elastic, whatever. The sum of all the potential energy and the kinetic energy equals mechanic. All the other kinds of energy that we can have in a material are non-mechanical. And heat energy is non-mechanical. But, nuclear, chemical, electrical, we can talk about like bond energy in compounds that can be broken. Yeah, it's not mechanical. Mechanical only deals with the kinetic and potential. In a world with no friction, we would conserve mechanical energy. We wouldn't lose mechanical energy. So initial mechanical energy would be equal to final mechanical energy. But we don't live, give me back my s orbital. We don't live in a world without friction. So what we tend to see is that we get transformations of mechanical into non-mechanical energy, and that usually takes the form of heat, and it's heat due to friction. So when we look back at our roller coaster, why is each successive hill lower? Because we're losing energy. And, see, and I even did it. We say we're losing energy. We're not. We're converting mechanical energy to non-mechanical energy. And that non-mechanical energy isn't going to do any work for us. It's not going to move the car. So eventually, you can't derive enough kinetic energy. Every hill has to be lower because there's a continual loss. If you touched the tracks after the roller coaster passed over, they'd be hot, because the frictional forces between the tracks and the wheels cause them to heat up, and that causes a loss of mechanical energy. Noise is also a loss of mechanical energy. That noise that you're hearing is actually air molecules being struck and moved, creating sound waves in the air, which is non-mechanical, because we can't use it to do work, but that's just another source of transfer out of the system. Now, this is kind of like all the problems where we ignore friction, we ignore air resistance, because we can do that because we're working at the high school chemistry level or high school physics level. If you go on and you engineer big systems, you can't do that anymore. But for our purposes, and as long as it's not a major transfer out of mechanical energy, we go ahead and we calculate final mechanical energy based on initial. And this is where you're going to find things you're going to absolutely love. If we have a system where the loss is significant, like a roller coaster has pretty significant transfer from mechanical to non-mechanical, then we can't use conservation of mechanical energy as a problem-solving approach. But, like I said, we ignore friction because we're working at the high school level. So when there is friction enough that we have to acknowledge it, we just talk about loss of mechanical energy or transfer from mechanical to non-mechanical. But generally what we're going to do is problems where that's not the case, and we can do some pretty neat tricks. So we're going to look at sample problem 5E. I'm not sure what page it's on in the new book, but you're going to like these and they're going to anger you. It zooms down the frictionless slide. The slide is 3 meters high. What's her speed at the bottom of the slide? She has a mass of 25 kilograms. So all these problems are based on this, that mechanical energy final equals mechanical energy initial. Darn it. And that mechanical energy final equals kinetic energy final plus potential energy final, and that mechanical energy initial equals KE initial plus PE initial. Now, in all the problems that we're going to do, one of those things, well, I shouldn't say in all of them. In most of the problems that we're going to do, one of those things zeroes out on each side. So when she's at the top of the slide getting ready to slide down, does she have any kinetic energy? Nope, she's sitting still. So that goes away. When she is feet on the ground, does she have any potential energy due to gravity? We didn't say there was a bungee on the kid. So what we find in this case is that KEF equals PEI. So what's the equation for kinetic energy? Well, 1/2 mass velocity, and in this case final, squared. And the potential energy due to gravity is mass, gravity, height initial. And obviously mass and gravity don't change. There's no initial and final value for those. Let me see if, there we go. Okay, we're back. So we're going to rearrange in this case to solve, of course, for VF. So a couple neat things happen. If we multiply both sides by 2 and divide both sides by mass, so we have 2 mass, gravity, height over mass. Well, mass goes away. It doesn't matter how much the kid weighs. And we need to take the square root of both sides, and that gets rid of that. So in this case, the final velocity is going to be equal to the square root of 2 times gravity times her height initial. So what's the final velocity? Well, square root of 2 times 9.81 meters per second squared times 3.0 meters. That's it. What do we get? So we get a final velocity with sig figs. How many did we have? 2? 3? We had 3. Okay, cool. I wrote it badly, but so VF equals 7.67 meters per second. Now, here's where you will be angry. All the projectile motion problems that you did can be solved this way. Not probably every single one of them. Many of them can be solved this way. I see the faces, I know, but you'll get to take your frustrations out on a flour bag, so that'll help. Yeah, it's kind of a bummer. And I've had students in the past who got sufficiently angry that they decided to go back and rerun these with the kinematics equations and see if I was telling them the truth, and they found that, yeah, I was. Sorry. Just didn't do anything to alleviate their misery. But, you know, you need to know both ways to get there. This is another one. All of the practice problems for 5E are assigned, so I'll cut you loose.